Okay, hello everyone, and welcome back to programming languages. And it's no longer semantics, we're doing verification now. So, welcome back to verification. And let me just start by saying that you should all have received the results of your first homework, at least the very first submission. Some of you are resubmitting and then might not have got the result of your resubmission yet. But if you haven't received any result for your first submission for the first homework, write me an email, there is something wrong. Uh, so that's that. And another thing that I wanted to say is a huge thank you to everyone who took part in the survey. Oh, so in the chat, there is a question, what is the deadline for resubmission? There is no deadline for resubmission. So we only have deadlines for the first submission, but the thing is, when you do resubmission, you will get results based on how much time I have. So there is also no guarantee that you get a fast reply for your resubmissions. How many resubmissions do we have? Infinitely many. So the only constraint is that I will probably answer the resubmission 2 or 3 days after you submit it. So that really makes the number of attempts finite, but other than that, there's no other constraint. Yeah, but don't really misuse this. And so let me share the screen. Some box here so that you can see what you guys say. Okay, so a huge thank you to everyone who took part in the survey. I'm making some changes based on your answers to that survey. So I'm just going to go over the changes and also over the things that I will not change. One of the requests that some of you had was to have coding homeworks instead of just theoretical homeworks. And this course is mostly a theoretical course. So, and there are students who are taking this course whose major is not computer science. We have people from mathematics. So I cannot have required coding homeworks, but I will give you the option of doing either the theoretical thing or a coding in some of the upcoming homeworks. And there was another request for having some doubt clearing sessions. And well, the original request was to have it on the weekends. Unfortunately, the weekends doesn't really work for me, but I can stay every Thursday after the normal session of our course, and you can ask any question that you have. And also this course is so small, you're just 17 students, so I can easily do one-on-one sessions. If you have any problem or any doubts regarding any part of the course, just write me an email and we can schedule a time to just meet either over Zoom or in person and have a one-on-one session as well. Another point is that I will provide lecture notes from now on, and these lecture notes will basically just contain some rigorous definitions and some of the proofs that are used in the lecture itself. But the course is not going to get more rigorous than what it is right now. There was one student who wanted the course to become much harder and more rigorous, and well, I can't do it because it wouldn't be fair to the others, but for that one student who wants that, you can do a PhD with me, because if you do a PhD with me, you have to go through all of these things in complete mathematical rigor. And so there were some clarifications asked about how the resubmissions work, which basically you have a deadline for submitting your first answer to every homework that I assign, but then after that, I will give you comments if you don't get 100%, and then you can resubmit, and there is really no limit on the number of resubmissions. And again, this works because the class is so small. What else? So there was a question about how the final exam works, and actually someone asked if we can have resubmissions of the final exam. So no, you cannot have resubmissions for the final exam, but the way that it works is that uh, I will give you a bunch of problems, probably 4 or 5, and you will have 2 days to write your answers and submit them to me. And I also just trust you that you will not collaborate with each other on that. Yeah, generally speaking, it's extremely easy to get an A from this course. Let me see what other comments there were. Oh, okay. So there was also a comment about the noise here, and they wanted me to change my microphone. The problem is not with my microphone. The problem is that there is a construction going out outside my window on campus, and this is the noise that you hear from outside. Okay. Yeah, so I just repeat this. You cannot resubmit your answers to the exam. The exam will have 2 days of time, but you can only submit the answers once. Okay. And now we can just go back to the course. So let me just give you a summary of what we already saw last time. I'm out of space, so let me just close the chat box. So basically, in the last lecture, we really started doing verification and came out of the whole semantics thing. So our focus is now on algorithms for proving correctness of the systems instead of focusing on what the systems or programs mean. And we defined the notion of infinite duration two-player games on graphs. And this was basically a graph in which we have 2 different types of vertices. In this example, I'm showing them with squares and circles. And the idea is that we have 2 players and each player owns some of the vertices. So one player owns the square vertices and the other player owns the circle vertices here. And we start the game at some point, at some vertex. We can call it B. And each player controls which outgoing edge we take out of their own vertex. So if we start here, the square player can choose the outgoing edge. For example, we can choose this one. And then the circle player chooses the outgoing edge from here, for example, this one. And then the square vertex chooses, and then the circle vertex chooses, and then the square vertex chooses. And in this case, because we come back to a square vertex, again, the square player chooses, and this goes on forever. And actually, in this case, he has only one choice. So we said that this infinite walk or infinite path on the game graph is called an outcome or a play, or sometimes we just say infinite path. So all these 3 things are the same: infinite path, play, or outcome. And also we define the notions of objectives and strategies and so on. So an objective was basically a set of infinite paths, a set of outcomes. And the idea was that each player has a desired set of outcomes and he wants to make sure that the outcome of the game is one of those. And we also defined the notion of a zero-sum game. We said that the game is zero-sum if the objective of one player is the complement of the objective of the other player. Or in other words, no matter what the outcome of the game is, one of the 2 players wins. This is what's a zero-sum game. And we also defined some classical objectives. We defined reachability, which is the objective that you want to reach a vertex in a given target set T. We also defined safety, which is basically that you want to always stay in the set T. You don't want to leave the set T. You want to be safe in there. We defined the bookie objective, which is that you want to visit the vertices in set T infinitely many times. We defined the co-bookie objective, which is that you want to remain in T after finitely many steps. So in a prefix of the outcome in infinitely many steps at the beginning, you can go outside of T, but at some point you want to come into T and remain there forever. And then we also defined parity, which was a much more complicated objective, and the objective there was that basically you assign some numbers to every one of your vertices, and you want the parity of the number that is repeated infinitely many times, the parity of the smallest number that is repeated infinitely many times to be even. And we also talked about how Buki and Kobuki are considered to be special cases of parity. Uh, then we went into defining what we mean by a strategy, and I'm going to review this one as well. So in our case, a strategy is basically just a function that gets the history of the game, and the history of the game is the path that we have gone until this point and the vertex that we are currently in, and then tells the player which outgoing edge he should take based on the strategy, based on the history of the game. And we said that a strategy is memoryless if it only depends on the last vertex. So if you have a strategy for one of the players that completely ignores what happened before getting to the current vertex and chooses the outgoing edge only based on which vertex you're in, that's called a memoryless strategy. And we also said that if you fix a single vertex and a strategy for each of the two players, then you will get a unique outcome, which we show with outcome of V, strategy 1, strategy 2. And based on this, we defined a winning strategy. And we said that a winning is that sigma 1 is a winning strategy for player 1 if no matter what strategy player 2 takes, the final outcome is in the objective of player 1. So the idea is that it's a winning strategy if it wins against any other strategy of the other player. And then we defined winning sets, and we basically said that a vertex is in the winning set of player 1 with a given objective if player 1 has a winning strategy from that vertex. And a vertex is in the winning set of player 2 if player 2 has a winning strategy from that vertex. And then we defined determinacy. And the definition of the determinacy was this. We said that a game is determined if from any starting state, one of the two players has a winning strategy. So basically, if the set of states from which player 1 wins is the complement of the set of states from which player 2 wins. And one thing that is really important, and I really want to underline, is the difference between being zero-sum and being determined. So these two things are not the same at all. When we talk about a zero-sum game, we are talking mostly about the objectives. We are saying that the objective of one player is the complement of the objective of the other player. But when we're talking about determinacy, what we're saying is that the winning set of one player, which is the set of states from which that player has a winning strategy, is the complement of the winning set of the other player. So make sure that you don't confuse these two things, because it's very common for people who work with games for the first time to confuse them. And I'm actually going to give you a homework on this. So this is the first homework from this module. I basically want you to provide examples of games, and by game I mean two-player infinite duration graph game. I want you to give me examples of games that are determined and zero-sum, non-determined and zero-sum, determined but non-zero-sum, and non-determined and non-zero-sum. So all four cases. So for each case, either you provide an example of a game that satisfies these conditions, or give me a proof that no such games exist. Okay, and the deadline for the initial submission for this one is 2nd of March. Okay, and just to make sure you understand what you should do here, basically I need you to give me a graph game, which is a graph and also the partition of vertices to player 1 vertices and player 2 vertices. And I also need you to give me an objective for each of the two players. So when I say give me a game, I mean both the arena and the objectives. Okay, and also in each case, when you're giving a game that is, for example, non-determined but zero sum, I really expect you to show why it is non-determined and why it is zero sum and so on. So really consider these homeworks more like math homeworks. Okay, so let's go back to where we left the last time, and this chat box is really annoying here, so try to put it there. It doesn't become smaller than it. Okay. So last time we were talking about reachability games. So the idea here was that, of course, we have a game arena and we have a set T of target vertices. And the objective of player one is to reach these target vertices. So we're talking about the reachability objective for player one. And you will see that during this course, whenever I don't say whose objective I'm talking about, I'm always looking at the game from the viewpoint of player one. So when I say this is a reachability game, I mean that the objective of player one is to reach some set T. Okay, we already saw kind of the way that we solved this in the last session, but I'm going to repeat some of it. And then we're going to look at it a bit more formally and also make it algorithmic. So suppose that we have two different players here. Let's say that player one is red, and let's say that player two is black. So the vertices of player one and two are here. We want to see from which vertices player one has a winning strategy, right? So the first obvious thing was that if you are already in the target set T, so in this case, this circle here, then player one wins because, well, in the very first step, we are already in T. And then we talked about this idea of creating an attractor. And the definition of attractor was this. The idea was basically, okay, if I know that I win from a given set, for example, if I know that player one has a winning strategy from A0, and if I have some other player one vertex, for example, this vertex here, that has an edge to the vertices from which player one wins, then player one wins here as well, because, well, player one can just start from this vertex. Choose a different color. Okay. Player one can just start from this vertex. Apparently, I can't change the color of the laser. And go to the vertex from which he would win, right? And we also had a similar construction for player two vertices. We said that, okay, if I know that I win in all of A0, and there is a vertex belonging to player two, but from that vertex, player two has no option but to go into A0, for example, this vertex, or this vertex, or this one, then I am sure that in one step, player two has to go to a state from which player one wins, and then player one can win from that state. So this is also a winning state for player one. So we basically had this definition, which we were saying that at each iteration, we define AN as the set of vertices from which we knew that player one would win anyway, which is AN minus one, union with the vertices that are player one vertices, but have at least one successor from which we know player one wins. So in this case, I can just go to that successor and win. And union with those vertices of player two, from which player two has no chance or no option other than allowing player one to win, other than going to a vertex that was already in the win set of player one. And then we said, okay, we create all these AIs, and, well, because in every one of these AIs, we know that player one wins, so we can just take the union of all of these sets and say that player one wins in all of them. And this is what I'm doing in this diagram here. So basically, A1 is created based on A0 and this formula, A2 is based on A1 and this formula, and so on. And then I'm getting the union of all of them. And this big circle A here is the set of all states from which player one has a winning strategy, right? Okay, now what is the winning strategy of player one? Well, it's just following these definitions. So if I am in a vertex in AN, and if I am player one, well, I know that I can go to AN minus one. So I can always go one step closer to the core, right? And if I am in a vertex in AN and I am player two, well, I have no chance but to go one step, at least one step closer to the core, because by definition, all of the successors go closer to the core. So the strategy for player one to win is to just, if you are in AN, find a successor that is closer to the core, that is in AN minus one. So in every vertex that was in this large circle A, we found an explicit winning strategy for player one. But this doesn't mean that these are all the vertices from which player one wins. We have to also prove that if a vertex is outside of A, then player one cannot win from that vertex. And we actually do this by showing that if a vertex is outside of A, then player two can win. And here I'm assuming a zero sum game. So I'm assuming that the objective of player two is safe V minus T, which means that player two wants to make sure that we always remain in V minus T and we never reach T. Okay, so why can he do that when we are outside of this large circle A? Well, let's see. If I'm outside of this large circle A and I am at a player one vertex, what does that mean? Well, by definition, it means that I don't have an edge to a vertex inside of A, right? Because if I had that, then this vertex would also go inside of A, according to these definitions here. So uh, as player one, I cannot go from outside of A to inside of A. But what happens if we have a vertex of player two outside of A, for example, this vertex here? Then again, by definition, there is a successor of this vertex that is still outside of A, because if all of its successors were inside of A, then we had to put this vertex in A as well. So what this means is that basically the set B, which is everything that is outside of A, this part, is a trap for player one. And what we mean by that is that player two can make sure that player one can never exit this set. So player two can always keep player one in this trap outside of A. And this is the strategy that player two can use to always win in the vertices that are outside of A. So what we did was that basically we could give a complete partition of the vertices of our game. And in some of them, we gave winning strategies for player A, for player one, and in the other vertices, we gave winning strategies for player two. So at every point of the game, we know exactly who wins. And also, we know that the game is both zero sum and determined. So why is the game zero sum? Because, well, this is based on the definition. The objective of player two, safe of V minus T, is the complement of the objective of player one, which is to reach T. And why is it determined? Well, because from every vertex, I could give either a winning strategy for player one or a winning strategy for player two. But this game is actually even more than that. It's even determined with memoryless strategies. So if you look at the type of strategies that I gave for the two players, the strategy for player one was always just looking at the current vertex. It was saying if you are in AN, if you are in a current vertex that is in AN, just find another vertex, another successor that is in AN minus one and go there. So the strategy didn't depend on what happened before in the game. It only depended on where you are right now. It was a memoryless strategy. And the same thing happened when I was giving strategies for player two. So the strategy for player two is that if you are in B, if you are outside of A, make sure you don't go inside of A. Always take an edge that keeps you outside of A. And this again doesn't say anything about the history of the game, has no memory. It's a pure memoryless strategy. Okay. Now, let's make this algorithmic. And making it algorithmic is not so hard, really. So, and by making it algorithmic, I mean that we want to have an algorithm that gets a game arena and also the set T as its input, and just outputs the sets A and B. So the winning set of player one and the winning set of player two. And this is also quite, I would say, standard in the way that graph algorithms work. So basically, if you have done queue-based graph algorithms, you will see that this is very similar. So I will have a queue, which I call queue. And initially, I just put the vertices of T in this queue. And then I have a set A, which is the set of vertices from which I know that player one wins. And initially, it's empty. And also, for every vertex, I just keep track of a counter, counting how many of the successors of this vertex are in the set A. Right? So while my queue is not empty, I just take vertices from this queue and put them in A. So for example, I start with here, I take one of these vertices, I say, okay, from this vertex, I know that player one wins. So I put this vertex in the winning set of player one. And then for every one of its predecessors, I update this value. So for this vertex, I say that now I know that one of the successors of this vertex is in A. For this vertex, I also say the same thing. So I just increase this. And then basically here I decide if the vertex has already become a winning vertex for player one. And the way that I decide it is that, well, if this new vertex is a player one vertex and it has an edge to a vertex that I know is already in V, so I know that I will win from here as well. So I just put it in my queue so that I add it later to A. And also, in any case, if all of the edges that are going outside of my current vertex, for example, in this case, all of the edges that are outgoing are going to A, then I also add the current vertex to my queue to be added to the set A. And then at the end of the algorithm, I just return A. Or to be more specific, I can return A as the winning set of player one, and I can return V minus A as the winning set of player two. Okay, so what is the runtime of this algorithm? Can you tell me in the chat, what do you think is the runtime of this algorithm? So to have some, okay, to have the same notation, let's say that our arena has n vertices and m edges. Okay, so there are different answers. There is both ON and OM. And actually the answer is order M. Well, if you look at this as only a graph algorithm, the runtime is actually order n plus m. Because if you look at it, every vertex goes into this queue at most once. And whenever a vertex goes into the queue, we basically check all the edges from its predecessors to it. So we are checking all of its predecessors. So this is equivalent to checking every edge once. So every vertex and every edge are used constantly many times, and the runtime is order n plus m. But okay, so one assumption that I maybe forgot to emphasize is that in the definition of infinite duration games on graphs, because we want our play to continue forever, we want to make sure that we don't have any dead-end vertices. So we have this extra assumption. We assume that every vertex has at least one outgoing edge. This is just to make sure that we always get outcomes that are infinite paths. And we don't really need this assumption in many cases, but it just makes the results more convenient. So let's assume this from now on. And with this assumption, then I can just say that the runtime is order n because I have definitely more edges than vertices. Okay, so we basically found a linear time algorithm for deciding reachability. And this is great because, well, in a sense, as I said in the previous lecture, reachability is used for bug finding. So if your two-player game is actually modeling, let's say, your program, and the two types of vertices that you have model different types of non-determinism in your program. For example, player one uh, is taking care of normal non-determinism, and player two choices basically model the non-determinism that happens because of user input, or the non-determinism that happens because of the environment. Then basically what reachability can answer is whether your program has a bug or not. As long as you can just say in which states T you consider your program to be buggy or wrong, then you can see if you can reach those bad states and whether your program can crash. Now, the problem here is that even though reachability has this really nice property, and even though we can solve it in linear time, again, uh, these are over finite graphs. So we still have the problem of translating our original program, which has infinitely many states, to a finite graph. And this is where you get really loss of precision. And you do, for example, abstraction, and then you lose some precision. But generally speaking, this is the runtime. And assuming a finite graph, you can basically find winning sets for the reachability objective in linear time. So what about safety? So what if my objective for player one, instead of reaching the set T, was to just stay in the set T and be safe there? What kind of algorithm can I have for this? Okay, so in the previous session, we actually talked about this, and the idea was that safety is a dual to reachability. And so basically we said that, well, if player one wants to stay in T, what does that mean? It means that, well, player two wants to definitely reach V minus T. So you just solve the problem from the point of view of player two. You say, okay, player two wants to reach V minus T. From which vertices can he do that? And then from all the other vertices, player one can just ensure safety inside of T. And note that what I'm using here in doing this dualization is actually the determinacy result. So if my game was not determined, I couldn't really just say that, okay, let's look from the point of view of player two and let's see from where player two can win, and then just complement it and we get the winning set of player one. So determinacy is a very important subject, and you should always take care of it whenever you're talking about any kind of game, not even just graph games. Any game that is zero sum, you have to make sure that it's also determined. Okay. Uh, so this was what I wanted to say about reachability, but let's now move on and let's talk about Bookie. But before we go to Bookie, I just want to define some really basic notation. So first of all, when we were doing reachability, we were doing this attractor sets, this definition here. So this was the definition of an attractor set, A. And this is the idea that we've talked about several times. Basically, you have this original set and you just create larger and larger sets from which you know that player one can force the game to reach the set T, right? So we have a new notation for that, and I write this by attractor one of T. So attractor one of T is the largest set of vertices from which player one can force the game to visit T. So it's the same as A in our previous algorithm. And based on this, you can basically define attractor 2 of T. So attractor 2 of T is the largest set of vertices from which player 2 can force the game to visit T. Right? And also we had the notion of traps, which are kind of the dual of attractors. And we said that a set is a trap for player one, keeping him out of T. If it's basically the complement of the attractor, it's the place where player two can make sure that player one will never reach T. But let's talk about the attractors mostly. So let's say that I have a game graph or an arena G, which, as you recall, is basically a graph with vertices V and edges E, and also the vertices are partitioned into two sets that belong to player one or player two. Now, I want to see when I can look at a subgame. Basically, when can I look at a subgraph of this original graph? So let's say that I have a set of vertices W that is basically a subset of V, and I want to create this subgame, which is basically the induced subgraph by W. So the set of vertices is just W. The set of edges, I just take every edge that has both of its endpoints in W. And then I don't really change who owns each vertex. So the vertices that belong to player one would be V1 intersection with W, and the sets that belongs to player two is also very similar. So when can I define such a subgame? Well, we had this extra condition on our arenas that every vertex should have a successor, because if a vertex didn't have a successor, then we ran into the problem that the outcomes of the game were not infinite paths. So this is the only constraint that we have here as well. So as long as the set of vertices W is chosen such that every vertex in W has a successor in W itself, then we can define a subgame arena based on W like this. Okay. So now let's just think about the set A that we created here in our reachability example. And let's also think about its complement B. And I want you to tell me whether A or B induce a subgame. So first of all, does A induce a subgame? Can I have G of A? Can I limit my game to only A? Well, and when I'm saying this, I don't mean in this specific example, I mean in general. So suppose that A is the attractor, is basically this, the attractor one of T. Does A always induce a subgame? So tell me in the chat, yes or no. So in other words, can I have G of A in the same way that I have G of W? So this is actually not a hard problem, because the question that I'm asking you is basically, if I take this set A, does every vertex have a successor inside A itself? Okay, we have one yes. Okay, two yeses. Anyone who says no? No one says no. Okay, the answer is actually no. And the reason is that we're pretty sure that all the vertices in AN have a successor that is in AN minus one, right? So we have no problems with these vertices. We have no problems with vertices that are in A1 to AN. The problem that we have is with the vertices that are in A0 or in T itself. So basically, I might have a case where a vertex in T has no other successor in T, right? So let's go back here. So for example, consider this vertex here. It has no other successor in T. Well, in this case, it has a successor in A. But instead of this edge, I could easily have just an edge to somewhere outside, right? Because I had no constraints on my T. So A does not always induce a subgame. There are cases where we can't just look at A and say we take this subgame. And that's because, well, the target set T itself can have basically an edge to B. Okay, how about B? Does B induce a subgame? Can we always have G of B? Okay, we do another poll. Who says yes? So remember that B is basically the complement of A, everything that is outside of A. So does every vertex in B have an edge to another vertex in B? And actually, in this case, the answer is yes. Right. So if you take a vertex that is in B, which is outside of A, there are two cases. Either the vertex that is outside has only, either the vertex that is outside is a player one vertex, in which case it has only edges to the vertices outside, and we know that it has at least one outgoing edge. Or it's a player two vertex, which by definition, again, has an edge to a vertex in B. So this works. And we have a question in chat that asks, what happens if B is empty? Well, if B is empty, again, this sentence holds, right? Because what we want is that every vertex in B has a successor in B. If B is empty, this sentence doesn't say anything because it's saying every vertex in the empty set. And then you can put anything there and it's still a true sentence. So it works for the case where B is an empty set as well. Okay, now my next question is this. So consider the set B. Is this? Consider the set B, which was basically the winning set of player two. And let's say that we take its attractor. So we compute the attractor of B, but we compute the attractor based on player two. So we compute all the vertices from which player two can force the game to visit B. Can we have a subgame on this attractor? So for example, here, in this example, this is B, right? And if I want to compute its attractor, it's all the vertices from which player two, so the black player, can force us to go into B, right? I guess there aren't many of those. This is a bad example. In this case, it's just B itself, it seems. Okay, so if there is, let's say, a black vertex outside, let's say there is a black vertex here, and it has an edge to B, then I would also put this in the attractor of B. And if there is a red vertex here, such that all of its edges go into B, then that's also in the attractor of B. In well, not exactly again. So there is a question in the chat that asks whether attractor 2 of B is always equal to B. Uh, Not necessarily. So let me show you why. Let me erase this. So basically, this again comes back to the problem that we have, that there is no restriction on the original set of target vertices on A0. So I can have a case where I basically have an edge, let's say, from this black vertex to somewhere in B, right? So if I have an edge from this black vertex, which was in A0 to somewhere in B, then this black vertex is actually in the attractor 2 of B, because remember, attractor 2 of B is basically all vertices from which player 2 can force us to visit B. And if this vertex here has an edge to B, then well, player 2 can choose that edge and force us to visit B. So you see that you can have a vertex that is in A and also in attractor 2 of B. So attractor 2 of B is not the same as B. But can we define a subgame on attractor 2 of B? So there is a question, only need one black vertex as some success. Yes, because, well, this is attractor 2, right? So the difference is that when we were defining A, we were doing attractor 1, and attractor 1 of T is the set of vertices from which player 1 can force us to visit T. Attractor 2 of B is the set of vertices from which player 2 can visit and can force the game to visit B. So that's the difference. So if you have a black vertex here, so black is player 2. If you have a black vertex that has even one edge to outside to B, then that's in attractor 2 of B. It's not in attractor 1 of B, but it's in attractor 2 of B. Okay. So basically the question is, if I take attractor 2 of B, is it the case that, yes, the thing in the chat is correct. So I'm asking, if I take the attractor 2 of B, is it the case that every vertex in this set, in attractor 2 of B, has a successor that is also in this set? And the answer is yes. Why? Because, well, it's very similar to what we were doing for A. And there, the only problem was that our initial set was not closed with respect to having existential successors. So the problem was that when we were computing this attractor of T, which we called A, T itself could have vertices that didn't have uh, any successors inside of T. But because B is not like that, then we don't have that problem with attractor of B either. So we can define a subgame on any attractor of B. Okay. Now I'm going to go one step further. So let's say that I take every vertex that is not in attractor 2 of B. So let's say that I define okay, let's say that I define V prime as V minus attractor 2 of B. Can I define G of V prime? Do we have this subgame? Okay. Isn't this just the second case? No, it's not the second case, because second case was just B, right? Okay, why no? So people who say no, why do you think the answer is no? Similar reason as G of A. So Well, that doesn't really work because when we were trying to do g of a, again, we had this problem with the initial case. We had this problem that we could have a vertex in T that has edges to only B, right? But we don't really have that problem here. So actually the answer is yes again. And to see this, uh, since I'm not sure if it's processed to reach. Okay, so let me explain it like this. So suppose we have any attractor. For example, we defined A as the attractor that player one has on T, right? So this is the attractor of player one that can attract everything to T. And when we got its complement, the complement of an attractor is always a trap, right? Uh, so A was an attractor in the sense that whenever I had a vertex in A, player one could force us to visit this set T. So A was attractor one of T. But then if I get the complement of A, which we called B, that complement was a trap for player one. It was basically the set of vertices that player two could make sure we never exit if we are there, right? Now this is just the dual of that. So what I'm doing is that I'm starting with another set. In this case, I'm starting with B instead of T. And player two is getting its attractor, right? So attractor two of B is the set of vertices from which player two can force us to visit B. But if I get its complement, if I look at V minus attractor two of B, that's a trap. It's a trap for player two. It's a trap in which player one can make sure that we never exit it, right? And because it's a trap, I can definitely define a subgame in there. So this one also works. So we have a question. So isn't this the same as the case two about B? Oh, right, right. Yes, I see your point now. Yes, it is the same as case two about B. So basically the idea is that, yes, if you just put T instead of B, this is the same as that. Yes. Okay. So what did we see here? We basically uh, proved the lemma. And the lemma was that whenever you have an attractor, its complement is a trap. And whenever you have a trap, you can basically limit your game to that trap and look at the sub game. Why? Because, well, if you have a trap, then one player can make sure that you never leave this trap. So it's very natural that it can be a sub game. Okay. So the first one doesn't work, but the next three work. Now, why did I tell you about all of this? So I told you about this because we want to use this in finding an algorithm for Bookie. So here's the idea, and this is the classical approach for solving Bookie objectives. So let's say that the objective of player one is Bookie of T. So I have a set T of target vertices, and what player one wants to make sure is that we visit this set infinitely many times. Okay, so let's just have a picture of this. Let's say that this uh, big rectangle is all of our vertices, and let's say that this is the target set. So using our previous algorithm, using the reachability algorithm, basically, we can compute the attractor of T for player one, and we called it A before. And then we could compute a trap B, which is the complement of A, and it's here. Okay. Now what I want to do is basically to do this thing here, taking the attractor of B itself. So let's say that C is the player two attractor for B. So C is the set of states from which player two can make sure that we can go to B. right? So if I want to draw this, this will definitely include all of B, because if we are in B, player 2 doesn't have to do anything, and we are already in B. And it will also include some of A and potentially some of T, right? So this would be the set C. Okay, and it includes all of B. I'm sorry for these things. Okay, so why are we interested in this? So let's look at the game with this objective from the point of view of player 2. And let's say that this is a zero-sum game. So what player 2 wants to do is that he wants to make sure that we do not visit T infinitely many times, right? So if the game starts somewhere in B, then by definition, we know that player 2 can do something such that we don't see T even once, right? Because A and B were the things that we obtained from our reachability game. So if we start the game from B, because B was a trap, player 2 could make sure that we never visit T even once. But what's the nice thing about C? Well, C says that, well, if we start the game somewhere in C, what we know is that player 2 can force the game to go into B. And in the path that the game takes, it might go somewhere in T, but then we know that after finitely many steps, it will eventually go to B, right? So we might visit some of the target states for finitely many visits, but then after a while, we will end up in B. And because we have ended up in B, from now on, player 2 can make sure that we remain in B, because B was a trap, right? So the strategy of player 2 in the set C would be to first force us to visit B, even if along the way we visit T, that doesn't matter at all, because we are talking about Buki, and the only thing that we care about is whether we visit T infinitely many times. So player 2 is fine with visiting T for only finitely many times. So if we are in C, player 2 first makes sure that we go into B. And then when we got into B, then he uses his strategy for trapping us there and just keeps player 1 spinning in B. So if the game starts anywhere in C, player 2 has a winning strategy. And I just told you this strategy, right? The strategy is to make sure the game goes into B, and as soon as the game went into B, just make sure that the game stays in B, because and he can do this because B was a trap. Okay, so basically what this means is that we have a very simple recursive algorithm. We know that in all of these vertices that were in C, player 2 wins, so we just mark all of C as winning set of player 2. And then we have the rest of the game. We have basically this part of the game. Right? I'm trying to use the laser. So we have this part of the game. And in this part of the game, we have to decide who wins, whether player 2 wins or player 1 wins, right? And we can do that recursively. So in this part of the game, we now have a smaller game and also a smaller target set. And we just do the same thing again. And we just continue this forever. Now, why does this make sense? For it to make sense, I have to make sure that this right part, this part that I'm highlighting right now, should be a well-defined game, right? And this is exactly what I did in the previous slide. So this attractor 2 of B is C, basically. And this V prime that I defined here is the remaining part, the right side part of the game. So this part in and of itself is a well-defined game. And So we have to also figure out what we want to do with the edges that go between the two parts, right? So first of all, let's see what we do if an edge goes from C to outside of C. So if I have an edge like this. So if I have an edge like this, there are two cases. Either the vertex here was a player one vertex, which shouldn't be possible, right? Because if that's the case, then C wasn't really the attractor to B. Because the idea was that by definition, if you start anywhere in C, player two should be able to force you to visit B. But if player one can just go over this border, then that means that player two couldn't uh, force the game to go to B. So we don't have this kind of edge with a vertex that belongs to player one. But we might have a vertex that belongs to player two and has an edge from the left side of the border to the right side. And in that case, we can just ignore that edge because, well, if we are already here, then player two has a winning strategy. And the winning strategy is to force everything into B and just loop inside of B. So why would he take this edge and go to the other side? He wouldn't do that. He would just play his winning strategy. So this edge is nonsense. We can just ignore this kind of edge. What about the other type? So let's say that I have an edge like this. Now, if I have this is the exact dual of what I said before. If I have a player two vertex here on the right side, and then I have an edge to the left side, then this is contradictory because then this vertex would be in C by definition of C because C is an attractor for player two, and then it would be in C. And if I have a player one vertex here, then it doesn't make sense for player one to take this edge because if he takes this edge, he goes into C and then from there player two would win. So again, I can ignore these edges as well. So basically what I showed you is that it makes sense to break this game into two different parts. And we know that in all of the vertices in C, player two wins. And we also know that if we take all the vertices that are not inside of C, if we take all the remaining vertices, this is a completely independent game. And no one would ever go from this game to the game in C. So we can just recursively solve this completely independent game here. Okay? So that's our algorithm. And we can also write this algorithm in a non-recursive manner. And the non-recursive manner is just following the recursion. So let's say that my original game starts with a game graph G0, which is the same as my original game, and with a target set T0, which is the same as the original target set. And let's say that I want to populate a set W2, which is basically the set of all vertices from which I know that player two has a winning strategy, right? So I just repeat this process, and the process is very simple. So at every step, I first do the normal thing that I did for reachability. I find the set A and B. So the set A is the set of vertices from which player one can make sure we visit the target at least once. The set B is the set of vertices from which player two can make sure that we will never visit the targets. So B is actually, in this case, I'm also using a subscript of the for iteration. So it's BJ instead of B. So BJ is a trap. It's a trap that player two can keep us in, right? And then we compute the attractor of this trap. So attractor two of this trap. And basically we know that anywhere in CJ or C, player two has a winning strategy because the winning strategy is just to, because it's an attractor, he can make us go into BJ. And then because BJ is a trap, he can keep us there. And this makes sure that we never visit T after we are trapped, right? Okay, And then, so I can just add these vertices in CJ to the winning set of player 2. And then the rest is just computing this game on the right side here. And the game on the right side was basically the game on the set of vertices from which C was removed, right? So this is that. I also need some sort of condition for ending this for, because I don't want it to go on forever. And for that, I can just simply say that if CJ was empty, just break, right? So if we didn't find any new vertices from which player 2 wins, we break. And then finally, well, W2 is the set of vertices from which player 2 wins. And then we let W1 just be the set of other vertices. Okay. Now, I hope you are convinced that whenever a vertex is in W2, so whenever a vertex is in this set C here, player 2 definitely has a winning strategy from that vertex. But the question is, if a vertex is not in W2, so here, would player 1 definitely have a winning strategy? Or is it possible that player 2 has a winning strategy from some other vertices as well? Or maybe the game is not even determined. So this is the question that we should answer. Does player 1 have a winning strategy from every vertex in W1? And again, let me just give you a picture of this. So we started with the set T. We computed the set A, which is the set of vertices from which player 1 can force the game to visit T. We also computed the set B, which was the trap, basically. So player 2 could always keep us in here and make sure that player 1 does not visit T. And based on this, we computed a bunch of sets. So we computed C1, for example. Then we computed C2. Then we computed C3, and so on. So let's say that this went on for n steps, and the largest set that we computed was Cn. So based on the proof that I just gave you, we know that any vertex that is inside any of these CIs, so starting with C1, any vertex that is inside of any of these is winning for player 2. So player 2 has a winning strategy in this whole area. Right? This is all player 2 territory. But our question is, what happens if a vertex is here? Okay. Now, if a vertex is there, first of all, note that it's in A. And because it's in A, it means that player 1 has a strategy to visit T. Right? And remember that we said that this whole game on the right, this whole thing, so everything outside of the Cn, is an independent game for itself, right? So in this independent game, player 1 can force us to visit a target set, a target vertex T, so somewhere here. Now, so let's say that he uses this strategy and visits T. Okay. After we visit T for the first time, there are two cases. So either the vertex that we are visiting in T is a player 1 vertex or it's a player 2 vertex. Okay. If it's a player 2 vertex, we are sure that it doesn't have an edge to the other side. We already know that. Okay. So we just let player 2 play whatever he wants. If it's a player one edge, we are sure that it has a successor in this game, so we remain in this part of the game. So the strategy for player one is just remain in this part. Now, what happens if player one just follows this simple strategy? So whenever you are outside of T, whenever you are here, just use the strategy for reachability and reach something in T. And whenever you are already in T, just make sure that you stay in the current game and you don't go to the left side. You don't go to any of these winning sets of player two. So basically what happens in this case is that we start somewhere, we visit T, and then we will remain in T for a bit. But as soon as we go outside of T, then again player one has a strategy to force us back into T. Then again we just go around in T, and again as soon as we go out, player one has a strategy to force us back. So as you see in this set in W1, which was basically the complement of all the vertices from which we knew that player two wins, we actually have a winning strategy for player one here. So again, we are back to the same case that we had with reachability. Basically, for every vertex, we either found a winning strategy for player two, or we found a winning strategy for player one. So the game is determined, and we could exactly find the winning sets of both players. Okay. Just one more point that I want to mention here is that the winning strategies that we just saw were actually memoryless strategies as well. Okay, how are they memoryless strategies? Well, let's first do the strategy for player two. The strategy for player two was if you are in B, make sure you stay in B. And this doesn't depend on the history of the game at all. It only just looks at the current vertex and makes sure that the successor that he chooses is also in the same set B. Okay. And well, the strategy in C1 was force us to go to B. So that's also memoryless. And you can just do the same thing in all of the cases where we had recursion, right? So you can do the same thing for C2, B2, and so on. So you can be sure that the strategy of player two is always memoryless. But what is the strategy of player one? So the strategy of player one was, first of all, we only care about it here because whatever he does outside of this point is in the left side is not really important because he's going to lose anyway, right? So we only care about his strategy in the right side game. And the strategy when you are outside the circle was to just reach the circle. And this is the same as the strategy for reachability, which was already memoryless. And when you are inside the circle, when you are inside T, the strategy was make sure you remain in the right side and you don't cross over to the other side. And that's also a memoryless strategy. It only looks at the current vertex and its successors. So overall, what we proved right now is that there is an algorithm for computing the winning sets for Bookie. And this algorithm actually also gives us strategies, and the strategies that it gives us are memoryless. And because every vertex is either a player one, because at every vertex either player one has a winning strategy or player two has a winning strategy, then the game is determined. So it's memoryless determined. Okay. Finally, I have a question for you. So what is the runtime of this algorithm that we have? So we basically are just computing we're basically just doing the reachability algorithm over and over again, right? We are basically computing attractors over and over again. And we already know that computing attractors takes linear time. So what is the runtime of this whole algorithm? Any ideas about the runtime? So let me ask you this instead. How many iterations do you think this for loop executes for? So what is the maximum number of iterations that this for loop can have? Yes, n iterations. Why? Because, well, at every iteration, we are finding a set Cj, yes, of vertices, and we are adding these vertices to the winning set of player 2. And as soon as we don't find any new vertices, we break. So we can add at most n vertices to the winning set of player 2. So this for loop runs for n iterations at most. And we already saw in the reachability algorithm that computing attractors takes linear time. So the overall runtime would be just order n times n. And we can also find the strategies in the way that I described. The game is determined, it's memoryless determined. And finally, when you want to figure out Kobuki, you just use dualization. So again, if you want to, let's say, solve the case where the objective of player 1 is Kobuki of t, well, this basically means that the objective of player 2 is Buki of v minus t. And you just solve that one instead. So you solve it from the point of view of player 2. So the same algorithm for Buki can also be repurposed for Kobuki. And in the next session, I'm also going to talk about how we can actually make these algorithms faster. So we want to make it order n squared instead of n times n. And then after that, we will go to parity. We are almost out of time. Are there any questions? Anything that was not clear? Okay, so let me just repeat some of the things that I said at the beginning of this session. First of all, every Thursday, I will just stay here for half an hour or 40 minutes to answer any questions or doubts that you might have. And also email me if you have any other doubts, and we can just, I might be able to answer it over email, or if not, I will just set a one-on-one session and talk to you about it. Okay, and that's all. Have a very good day. See you on Thursday.